Hi everyone, I'm Mr. Fullerton, and today I'd like to talk to you about characteristics of waves. Our objectives are going to be to define terms used to describe periodic waves. Terms like wave speed, wave velocity, wavelength, frequency, even period of a wave. We'll also determine whether points on consecutive waves are in phase or not. So let's start off by looking at a transverse wave. And if you recall, a transverse wave is a wave in which the direction of the wave's velocity is perpendicular to the direction of the movement of the particles of the wave. So, if we have a transverse wave, we can label a number of points on the wave. The high points or peaks we call crests, and the low points we call troughs. The amplitude of a wave, which is how much energy it contains, is a measure from the baseline to the crest or the baseline to a trough. Either way, we'll label that with the capital A, so that could be the amplitude or that could be the amplitude. And it's the magnitude of the distance between the baseline and the crest or the baseline and the trough. Wavelength is the distance between the same point on two consecutive waves. So a wavelength could be measured from crest to crest, that distance, and we'll label that with the Greek letter lambda, L-A-M-B-D-A, if we want to write that in English. The lowercase lambda tells us the wavelength, the distance between 2 points, the same point on consecutive waves. Now, period is the amount of time it takes for one wave to go by. So pick a point in space, the time it takes for one complete wavelength to pass is the period. We call that capital T, and you may recall that from mechanics, where that was the time for one complete cycle or one complete revolution when we were talking about circular motion. And frequency, then, is 1 over the period, which is the number of waves that pass a given point in 1 second. And period, likewise, is 1 over frequency. As we look at longitudinal waves, that means the wave velocity is in one direction and the particles of the wave vibrate in that same plane, parallel to the direction of the wave velocity. We can label the parts on a longitudinal wave as well. Areas of very high density we call compressions, and areas of low density we call rarefactions. Amplitude, again, is related to the energy of the wave. The more amplitude, the more energy there is in the wave. And in this case, it has to do with how dense the compressions are and how non-dense or less dense the rarefactions are. Wavelength we measure the same way. Take the same point on consecutive waves. So we could go from compression to compression in order to find our wavelength, or you could go from rarefaction to rarefaction. And frequency and period apply here just as they did when we talked about transverse waves. So, sample question 1. The diagram represents a transverse wave. The wavelength of the wave is equal to the distance between which points? It means we have to find the same point on consecutive waves. If I look at A, I can see the same point over here at E. So the distance between A and E would give us a wavelength. I also see here, if we start at B, we have the same point on a consecutive wave there at F. So B and F should work. Or if I start at C, the distance between C and G is the distance between the same point on consecutive waves. So I see 3 sets of points you could use to determine the wavelength here. Question 4. The distance between which 2 points on the transverse wave identifies the amplitude of the wave? Well, if you'll recall, the amplitude of the wave is the distance from the baseline to a crest or the baseline to a trough. So our choices between A and B, no, that doesn't work. Those are on the baseline. Between A and C, those are also on the baseline. A and E, there's the distance between a baseline and a trough. So that should work. There's our amplitude. In choice 4, D and E, well, that's from a crest to a trough, so that would be 2 times the amplitude. That can't be the answer. Correct answer must be 3, A and D. A periodic wave is produced by a vibrating tuning fork. The amplitude of the wave would be greater if the tuning fork were struck more softly, struck harder, replaced by a lower frequency tuning fork, or replaced by a higher frequency tuning fork. It's interesting here, in this problem, they talk about lower and higher frequencies. Note that when you hear a sound wave, higher frequency corresponds to a higher pitch. Lower frequency corresponds to a lower pitch. That's not going to help us, though. If we want the amplitude to be greater, we need to put more energy in it. We get more energy, more loudness, by striking it harder. So the correct answer must be 2.